Thank you very much. And thanks to the organizers for a conference that's been run very smoothly. Great venue. Um, and thanks to the program committee for a really interesting choice of talks. And also for choosing my talk. So this is joint work with Cosmin and John Van de Wettering. You can see the archive posting here. If you want to get in touch with me, there's my email address. So apologies for the slightly technical talk. I'm going to define all of these things, and I'm going to make them hopefully much more information theoretically appealing and intuitive. So the main result is a new characterization of quantum theory within a much broader framework, which is known as nowadays as general probabilistic theories, although it has roots in von Neumann's work from the 30s on quantum logic, and a lot of work in the 1960s, especially by Fallis and Randall at UMass, Gunther Ludwig in Marburg, and many others. But this area has been kind of revitalized by the advent of quantum information, in that now we might want to look for information processing principles that could help us characterize quantum theory. The principles we're going to use are homogeneity, which basically in information theoretic terms says that the probabilistically reversible transformations of a system act transitively on the strictly positive states, so the interior of the state space. And the boundary is measure zero, so in some sense, up to experimental error, all the information is in the structure of the interior. We also have pure state transitivity, so the reversible transformations, deterministically reversible, can take any pure state to any other pure state. Now, I mentioned self-duality and the Jordan structure. These two get us the Jordan structure, and therefore the self-duality. And earlier work by myself and Cosmin and Marcus Mueller, we used energy observability to then go further and narrow it down to complex quantum theory. So, the general research program, which I recommend as something you can do in conjunction with quantum information at a lot of groups. And you'll learn a lot of mathematical tools that are also useful in other areas like convex duality, probably Lie algebra, Lie group theory. In this program, research program, we use an abstract framework for describing systems in terms of probabilities for processes. We want to characterize quantum, maybe classical theories, within a much broader class of theories, and perhaps get principle-based formulations of quantum theory. Some people even think maybe this is going to lead to something like the Einstein's formulation of general relativity in terms of simple principles. Although, in a sense, we've got an embarrassment of riches here that by now we have many different formulations of quantum theory in terms of information theoretic principles. We want to understand how the possibility and impossibility of information processing protocols, is connected with properties of state spaces, measurements, their dynamics, and perhaps do the same for physical phenomena like thermodynamic behavior, time reversal symmetry, and so on. Okay, so I'll say a little bit about how we get from complex general probabilistic theories to complex quantum theory. It's very common that you go through first characterizing some class of Euclidean Jordan algebraic theories. And that's already almost quantum theory. It was formulated as a possible abstraction of the Hermitian matrices by Jordan in 1933, who hoped it would be a good framework for quantum theory. Shares most of its properties, like spectral decomposition, a trace. And Jordan, von Neumann, and Wigner in the 30s classified the finite dimensional Euclidean Jordan algebras, and they're just real complex and quaternionic quantum theory. Systems whose state space is a ball, which are known as spin factors, and three-dimensional octonionic quantum theory, which is the exceptional Jordan algebra. So, how do we get from this already close to quantum class to quantum theory? Well, you have various options. Energy observability is one, which, it's a Noether's theorem-like correspondence between the generators of reversible dynamics and observables conserved by the generated dynamics. Anti-Hermitian generators of the reversible transformations in quantum theory, the unitaries, and Hamiltonians, Hermitian operators. Multiplication by I is the correspondence. There's also locally tomographic composites. So if you have a way of making a composite system where Alice and Bob can look at the statistics of joint measurements on many copies and determine the state, that really only works in the complex case. Maybe existence of sick POVMs. It's known they don't exist in the real case. Okay, sometimes you still have classicality left, and we know many simple ways of ruling out classicality, like no information gain without disturbance, or the multiple decompositions of mixed states into pure states. Okay, so some background notions. A convex cone is just a set that's closed in a real vector space, a set that's closed under non-negative linear combinations. And we typically assume they're regular, so they're pointed, they have no full line, topologically closed, and spans the space. And that makes the space an ordered vector space, right? Just like Hermitian matrices are ordered by their positive semi-different cones. If the difference is in the positive cone, then X is greater than Y. There's a dual. It's just everything in this dual space of real valued functions, that's non-negative on the primal cone. And typically we like to think about operationally meaningful processes as affine because we want to conserve convex combination. If you're having something happening conditioned on something that you don't know about, you would like your probabilities to be the average of what you would have if you knew this unknown thing that you've conditioned on. Okay, so the general framework is very similar to quantum theory in the mixed states formalism with CP maps and so forth. We just got normalized states instead of the density matrices, an arbitrary convex compact set, which I like to call omega. Pure states with extremal elements, you can't write them as non-trivial convex combinations. Unnormalized states are this cone of non-negative multiples of the normalized states, positive semi-definite matrices in the quantum case. So that's why we mentioned cones. Probabilities are just given by evaluating elements of the dual cone on the primal cone, and these elements of the dual cone should take probabilities as values. So they should be below some functional u, which is the unit effect. It's the functional that takes the value 1 on all normalized states. The trace in quantum theory. Complete measurement, bunch of effects that add up to this unit measurement, just like POVM. Unnormalized effects, they're the dual cone to the state cone. Strictly positive states, are the interior of this state space. And that means they've got, they never give probability 0 for a non-trivial measurement. Okay, so that's the formalism. Here's some examples. State space of a rebit, a classical bit, a classical trit, extreme points or pure states in red, a squit, square bit. Red is not the extreme points here. This is like one wing of a PR box, right? That's its state space. So we can use this formalism, for example, to study stronger than quantum correlations. I just embedded them here as the base of their cone of unnormalized states, so you get an idea what that looks like. Here's what the sets of effects look like. They got to be positive, so they should be in the dual cone. Turn the dual cone upside down, put its point at the unit effect. That tells you the probabilities are always going to be less than 1. So you get these things for a classical trit. It's the cube. Here's the unit. Okay, just have a little visual intuition going on. Okay, so now we need to introduce a concept called self-duality. You might have noticed that in the quantum case, both the effects and the states are represented by Hermitian matrices, and we use an inner product to determine probabilities. So we're basically representing the dual space in the primal space by means of that inner product. And so the dual cone internal to that space is the one where it's everything that's got a non-negative inner product with the primal cone. In quantum, it's self-dual. We've chosen an inner product, the trace inner product, such that the state cone is equal to the effect cone. It's a very, very unusual property. it's not even equivalent to the state cone being affinely isomorphic to the dual cone, which we call weak self-duality. Because, for example, the cone with the square base, you set it up with a positive definite inner product. The natural inner product is going to have the dual cone rotated 45 degrees. Isomorphic, but you can't make it identical. And generically, you don't have either of these properties. Okay, we need to also talk about reducibility. Basically, if you can split up the vector space so that all the pure states are in one subspace or another subspace, then which of those subspaces you're in is classical information. All states are convex combinations of something in one or something in the other. And you can, so if you don't have that, the cone is irreducible. You can't split it up. Every finite dimensional cone decomposes uniquely into irreducibles. So we think of those as super selection sectors, classicality. It's going to appear in some of our results. Okay, and so, you know, a product algebra is just you take the direct sum of the vector spaces, you take the product component y's extended by bilinearity, and for a Jordan algebra, the positive cone, which is the cone of squares, reduces as a direct sum of cones. So simple Jordan algebras, which don't have any such product decomposition, those have no classicality in them. Okay, we also have dynamics are going to be important and possible symmetries. So we want to look at maps on this state space. And it's just very similar to quantum mechanics. Positive maps just take the cone into itself. Potential deterministic cones, they should take the cone into itself, but also they should preserve, they should take the normalized states into themselves. So U of phi of omega should be 1 for every thing that starts out with U being 1. Just trace preservation in quantum theory. So, okay, these, sorry, those are potential deterministic evolutions, not necessarily reversible. They're reversible if they take the normalized state space onto itself. In quantum theory, just unitaries and the transpose. Okay, we don't use the transpose, but it is reversible dynamic, potential reversible dynamics, a symmetry anyway. Potential probabilistic evolutions, we just want them to be normalization non-increasing. And the probability of that evolution happening is just evaluating the norm after you've applied it. Okay. The order automorphisms is a very important notion. Are the symmetries of the unnormalized state cones. So they have to take the unnormalized states onto itself, but they don't have to preserve the base omega of normalized states. And in quantum mechanics, what's that? Rho goes to A rho A dagger, where A is a non-singular matrix, so single, non-singular Krauss operator, and the transpose is there again. Okay, and so it's an easy proposition that the normalization non-increasing order automorphisms are precisely the probabilistically reversible dynamics. And what we mean by that is that it takes, you know, with some probability, you can reverse it, and you know you've reversed it. Useful notion in a lot of information processing protocols. Okay. So now we can define one of the key principles we're using. That's homogeneity. A cone is homogeneous if the group of order automorphisms acts transitively on the interior of the cone. So it can take any interior point to any other interior point. In the quantum case, it's easy to prove. If you want to take x to y, and they're both non-singular, which is the interior, then you just take x to the minus 1/2 followed by y to the 1/2 as your Krauss operator, and it's pretty obvious that kills x and replaces it with y. And it works the same for the other matrix Jordan algebras. You need real or quaternionic matrices. For the spin factors, this is a ball, and you're basically dealing with the Poincare group as your automorphism group. That's going to act transitively on this sort of generalized light cone in p space and 1 time dimension. And it's easy to show that it's preserved under direct sum. So in particular, the classical cone, which is just the non-negative orthant, is homogeneous. Okay, an important theorem by Koescher and Winberg is that every finite dimensional self-dual homogeneous cone is actually the positive cone of a Euclidean Jordan algebra. Um, our main theorem is a very similar result, but we replace self-duality with pure transitivity. So it's the transitivity of the deterministically reversible transformations on the pure states. For some base of the cone, which we interpret as the normalized states. But if it's true for one, it's true for any. Okay, just a note, this is pretty non-trivial because non-self-dual homogeneous cones exist in profusion. There's a continuum of them if the dimension is higher than about 5. And Hideyuki Ishii has even shown that there are weakly self-dual, non-self-dual ones of arbitrary rank, and that means arbitrarily number of distinguishable states, so arbitrary information capacity. Okay, so now a restatement of our main result. We have reversible transformations acting on the pure state. We could confine ourselves to the connected identity component of the automorphism group acting transitively on pure states. If we wanted, that's a stronger assumption. So the theorem is if we've got pure transitivity and homogeneity, we have a product of isomorphic simple Jordan algebras. You can think of that actually as a combination of a classical system, which says which isomorphic Jordan algebra you've got, and a particular Jordan algebraic system. If it has continuous pure transitivity, it's got to be the state space of a simple Jordan algebra because you can't get between classical sectors continuously in finite dimension anyway. And this all assumes finite dimension, by the way. The proof uses these two references. And really, Winberg did most of the heavy lifting, I have to say, but it takes a while to understand his paper. Okay. So an information-focused restatement of it is we can reformulate homogeneity as saying every strictly positive state, so interior state, can be taken with non-zero probability to any other such state up to normalization by a probabilistically reversible operation. And the reason is it's an easy proposition that the order isomorphisms are precisely the non-negative multiples of the probabilistically reversible transformations. You see, the problem is you can obviously, if you can go from any interior point to any other interior point, you can obviously go to any multiple of a normalized state, to some multiple of any multiple of a non-normalized state, actually, by an automorphism. That might not be a legitimate trace or a normalization non-increasing thing, but you just need to shrink it enough and it becomes trace non-increasing, basically because there's a maximum expansion factor over the compact state space. And then you can just do the same thing for the inverse and get a multiple of the inverse that is reasonable. And there it goes. Okay, so what's a motivation? What are some motivations? Well, a lot of people just use continuously reversible transitivity. Hardy, in about 2001, classic paper, was one of his assumptions. You might want continuous reversibility because of the continuous nature of time. Von Neumann used it in his argument that the quantum von Neumann entropy was thermodynamic entropy. And even the non-continuous version enables teleportation in suitable composites. So here's the reference. And of course, rather trivially, it implies the existence of a unique maximally mixed state just by group averaging, invariant under reversible transformations. So the point is, although in any GPT, you can prepare an arbitrary state from any other state, that's an entanglement breaking, coherence destroying channel. Automorphisms are intuitively maximally entanglement preserving and coherence preserving. So preparability of every maximally informative state from every other such state by an automorphism is a very unusual property, and it's important for coherent information processing protocols, such as steering and teleportation. So here's a little bit about steering, and it's pretty much based on this paper by myself, Philip Gabler, Alex Wills from 2009, 2013. We related homogeneity, Schrodinger-style steering of marginal states. And what's that? You want to make any ensemble for the one marginal of a bipartite state as the conditional states of a measurement on the other part of the bipartite state. And you can kind of see that's related to automorphisms because, you've got a map induced by the conditioning map between effects on one side, measurement outcomes on one side, and gives you a conditional state on the other. And if that is an automorphism, that actually allows you to take POVMs to ensembles bijectively. So that's roughly how that works. This is also related to very closely to the unique purifiability up to level symmetries postulate, as we point out, and that was used in important work by Kiribella, Dariano, and Perinati, which I urge you also to look up. So the theorem, we have a slight strengthening in the new paper. In any theory with universal uniform steering, so for every system, there's another system that is capable of steering any state in the first system, where the steering system is the same dimension as the steered system. For instance, if you could use the same system, a copy of the same system, every irreducible finite dimensional state space in the theory is homogeneous. So just one example of several connections. And I just, as a final thing, we talked about possibility and possibility of information processing protocols. So I just want to note that steering is the key to defeating the Bennett-Broussard type bit commitment schemes. So we're making connections between information processing and the structure of state spaces. Thank you.
Thank you very much for the talk. Do we have some questions from the audience?
Thank you for the nice talk. So my question is so I sometimes wonder how can we calculate, how can we understand more operationally as what is a homogeneous in the model? And you just answer one with you give one with the answer that you can derive the homogeneity by the universal steering condition. So
by which condition?
A steering condition you mentioned.
Yes.
Yeah.
So, unfortunately, it's not quite if and only if, but
yes. Is there any other condition driving the homogeneity?
So, I guess I wouldn't say that I necessarily know of any, although it would likely be useful in teleportation as well. Yeah, I mean, it does have a little bit more. Describing it as probabilistic reversibility does give it a more intuitive flavor than I think just talking about transitive action on the interior of the cone. So I wanted to point that out. But other than that, I don't really know any, although I would look at teleportation, because teleportation also uses kind of an automorphism identification. I mean, the information kind of goes through the dual space and then back into the primal space via the other EPR pair.
Thank you so much.
Thank you.
Hello, thank you for the talk.
Thank you.
You mentioned in the beginning like a principle theory. I understood it as a theory of empirical principles. Did I get that right? I mean, like special relativity, empirical principle of the constant speed of light, and the relativity principle.
Yeah, roughly.
Okay. And can you say something more? How would you now formulate a principle theory that explains quantum mechanics from your homogeneity, or what would you use?
Well, so I'm not sure we're completely there yet, although I mean, I guess one thing would be talking about reversible operations being powerful is kind of a set of principles, and also having the observability of energy, that Noether's theorem type thing. It might be a natural principle, perhaps not quite as natural as the formulation of special relativity. And it's just kind of a strange thing, because we've ended up with many different small sets of principles that characterize these Euclidean Jordan algebras, and therefore quantum theory. You can look at, I think if you look up, most of the authors I've mentioned have some result like that. So sometimes I like to joke that this is a cubist with a C view of quantum mechanics, because we look at it from many different perspectives and it's the same thing, but we learn different things about it. Of course, the cubists with a Q, at least one of them, named Chris Fuchs, thinks that most of these don't have enough of what he calls zing. He's still looking for the thing that's going to be it.
Thank you for the talk. I think I have two kind of related questions. One, could you just mention about the tensor product structure? Do you get it for free? Because in general, we know you get more than one tensor product in principle, but here I think you get the kind of the quantum tensor product. And related to this, on your slide of dynamics, there was no mention of kind of complete positivity, and I guess it's related to this. Like, do we need to be worried about dynamics which are completely positive, and you had the transpose, for example?
Yeah. So one important point is that if a cone is homogeneous, it's homogeneous under the connected identity component of the automorphism group, and the transpose is not in that component. So any information processing that comes just from homogeneity, you can do it without the transpose. So that's good. Of course, we throw out the transpose when we start thinking about composite systems because it becomes inconsistent with composition. Yeah, in general, you have this minimal tensor product, this maximal tensor product, a beautiful result by Ludovico Lamy and Aubrin and Charek showing that they're equal if and only if one of the systems is classical. And of course, the minimal tensor product is you take only the product effects and all the states that are positive on that. You do kind of the opposite product states and any amount of entanglement and effects. Those are kind of the two things that bound the possibilities for a locally tomographic tensor product. In quantum theory, we end up in between. And it so happens that it's not that easy to make composites of these Jordan algebras. You have to add additional dimensions. And then local tomography fails because there's like global things going on. The easiest example is in real quantum theory, you have Y tensor Y, which, you don't have Y for a single, Pauli Y for a single, because it's antisymmetric, but you do have its tensor product because that becomes symmetric again. Yeah, so having good composites often is a huge constraint on having a decent theory where you can have many systems and start combining them and doing things that way. This is all single system stuff here, except for the local tomography.
Okay, the last question.
Yes, hello, thank you for the talk. So you talked about evolution in terms of maps.
Yes.
And so I'm wondering when is it possible to talk also of evolution in terms of a generator of evolution, like a Hamiltonian, for this kind of GPTs, or are there any conditions for this to be possible?
Well, yes, you need a non-trivial. I mean, you need the automorphism group of the normalized states to have a non-trivial Lie algebra, basically. So if you assume, for instance, this continuous reversible transitivity, then you get that. And of course, in finite dimensions, that already rules out classical, because classically it's just the permutation group. So yeah, in studying the symmetries, the Lie algebraic structure is actually very important. And of course, relating this Noether principle, or what we called it energy observability, is indeed precisely about that, about the generators of continuous evolution. Thank you very much.